Well, I think let's just wait for the last picture.
Okay, take your seats quickly.
Right, thank you very much. Syntax matters. People care about how their programs look like, and they should, because they read and write code every day. And therefore it's no great surprise that there are many syntactic extensions for Haskell out there. For example, we have do notation, right? Probably the most popular and prominent syntactic extension of the original Haskell. But also there's list comprehensions, we have arrow notation, view patterns, and all of these are supported by GHC, right? But on the other hand, there are also external preprocessors that people write to extend Haskell, to have their own syntax and translate their syntax into a Haskell program. For example, there's item brackets by She, there's HSC to HS, which you can use to generate foreign function interface, well, describe them. There's the Alex and Happy Lexer and parser generators, which essentially declare in DSL domain-specific language with the declarative syntax and generate a Haskell program from these declarations. Well, and in GHC 7.6, actually, we got two new syntactic extensions, lambda case and multi-rate if expressions, right? So these are syntactic extensions, but we also have syntactic abstraction. And these are good for increasing the expressivity of programs. And we just saw an example of exhaustive use of syntactic abstraction to generate code. But there are many examples out there, and most prominently, template Haskell provides this support. And on Hackage, there are 365 packages that depend on template Haskell. But also already today, we saw at least 3 talks, I think, where the authors use template Haskell to generate at least some of the auxiliary code. So it seems that syntactic extensibility and syntactic abstraction, that there is this static demand of having such features in a language. When we think that the existing mechanisms for realizing syntactic extensibility and syntactic abstraction, that these are not satisfying enough. We propose something else. We propose an extension of Haskell to rule all the other extensions. So we want to have a syntactically extensible language, and we call this language SugarHaskell, and provide syntactic abstraction, but these syntactic abstractions, they can have arbitrarily context-free and layout-sensitive syntax. Extensions are composable. That means that as a user, I can use different extensions in a single module even. Also, the system is self-applicable, which means that if I define a language extension, then other extensions can be written with this language extension. And finally, we want to have some principled manner of dealing with all this flexibility. And therefore, we propose to scope syntactic extensions via the module system of the language. So let's look at a couple of examples. Say we have different syntactic extensions for applicative, for arrows, Happy, XML, and we organize them in modules or libraries of the language. Now, in order to activate such an extension, we simply import the library. So in this example, we import the control arrow syntax library in addition to the control arrow library to bring into scope the semantics, but also the syntax of arrows. And just after we do that, we can use arrow syntax in our program. And I said before, you can also compose different extensions. So let's say I want to use arrows to generate an XML document. So that's quite simple. I just import 2 different language extensions. In this example, I import arrows and XML. I can use arrows to, for instance, query an existing XML document, and then I splice this information into another XML document that I generate, but I use, again, concrete syntax to describe this generated XML document. So let's see how this works. We organize language extensions in libraries, and we call these libraries sugar libraries. And the sugar library consists of 2 components. First, it defines the syntax, and then it defines the desugaring. The syntactic definition, it defines the extended syntax and how this extended syntax integrates into the base syntax of our language. The desugaring is a transformation that takes input or a program that uses the extended syntax and translates it into core Haskell syntax. So let's go through this with an example of error in the syntax. The first thing we do is we define the syntax, and for that we use a domain-specific language, which is similar to EBNF, but called SDF. And the main difference is that the non-terminal which we define is on the right-hand side of the production. So for instance, the first line says that if you have the keyword proc, followed by a Haskell pattern, followed by arrow symbol, followed by a command, and this is a new form of valid Haskell expression. Whenever the parser expects a Haskell expression, he can also now pass a proc command. The other four productions, they are used for describing the arrow syntax itself. We have, for instance, arrow application, we have like a binary application of a combinator, you have if then else. It's fairly standard. So the second part is we need to now be able to translate this extended syntax back to Haskell space syntax. For that we have a desugaring. And desugaring is also written in domain-specific language, which is called Stratego. Stratego is a generic programming language where you can write like generic traversals and stuff like that. But also you can write concrete syntax in the transformation, which is very useful. For example, here we have the sugar arrow transformation. And, well, we pattern match on a domain-specific program, or on a program from the extended language, such as the proc command. And we bind in this pattern match in this concrete syntax, we can escape to bind variables. And we can use these variables in the template to generate code. So in this example, we translate the proc command, which we introduced ourselves, into the basic arrow combinators, which are part of the arrow library. But then we can have many of these rules, therefore we also need to declare which rule should be applied automatically by the compiler. This is like the main entry point into our transformation program. For example, in this code we have like the free pathvars rule, which like collects all the free variables in the pattern. And we don't want the compiler to apply this, so that's why we also declare a rule that is applied automatically. Well, we can use all of this. We can import the control arrow syntax, we saw this before. Now the nice thing is, since we scope all the language extensions by the module system of the language, the language extension is only active when imported. There's no like global build script or anything to kind of couple the preprocessor or however you want to implement your language extension with the program. Well, furthermore, all our syntactic extensions are essentially syntactic sugar. And that's very useful because it means that to a client of our program, this is completely transparent. We can use any kind of syntactic extension and desugar us back to basic Haskell syntax. We compile it with GHC, and then the syntactic sugar is gone. Clients won't notice. Well, also, you probably noticed that, well, I didn't remove like the arrows and arrow combinators or anything. So you can always choose not to use syntactic sugar. So it's up to you to use it or not. You just offer like an alternative interface, which in many cases is more convenient. But if you were very careful, I kind of rushed over a very important technical detail. Namely, we have layout-sensitive syntax here. In the arrow notation, you can have a do, right? And this do, there's layout-sensitive syntax, meaning each statement needs to follow the offset rule, and all the statements need to be horizontally aligned. So we had to develop a mechanism that supports syntactic extension, where you just write a couple of new productions that integrate it to the existing kernel, but still is layout sensitive. And the goal is, since we want to like enable users to write language extensions, we want to have a declarative formalism. And our idea is that we define not the lexer for saying how the layout should interact with the parser, but we specify the layout as constraints in the grammar itself. We say which kind of shape, which two-dimensional shape the program needs to adhere to in order to be valid according to the layout rules of our language. So, for example, down here we have a single statement using arrow notation. And we use different selectors to address different positions in the shape. We use the first selector to address the first token of this tree. And we have the left selector to address the leftmost token that is not on the first line. Using these two selectors, we can specify a constraint very easily that exactly models the offset rule. We can say that the first token of this tree needs to be further to the left than the leftmost token of any other line. But for this tree, this is true. But let's look at another example. If we would have indented the third line not enough, but it would be on the same indentation level, on the same column as the first line, then if we would check this constraint again, it would fail, right? Because first.call is equal to left.call. Now we put these constraints into the kernel. When you say, well, I have an arrow statement and I want to use it inside an implicit layout block, then you need to say, well, this statement needs to satisfy an additional constraint. Maybe it needs to satisfy the offset rule. This is not the only layout constraint that we need. We also need to assure that if you have multiple statements, they are horizontally aligned. And for this, we use a similar rule, but it relates the position of two trees, right? It not just constrains the shape of one tree, but two. So here's how this looks. You have two statements, and we demand that the first token is on the same column in both of these trees, so they need to be horizontally aligned. Well, to support this, we developed an extension of a generalized parser where you can annotate these constraints. And we have a paper that details that and also has an evaluation, like measuring the performance at SLE. And the core idea is some of these constraints we can actually check while parsing. And this is totally essential because otherwise it would be just too slow. So some of these layout constraints are context-free in essence. We can check them while parsing, while others, like the offset rule, is context-sensitive. We need to defer to after parsing or have a context-sensitive parsing algorithm that is efficient. And we don't have such a one. So we evaluated that by implementing Haskell 2010 kernel. And we passed almost all of Hackage. A few bugs that we need to fix though. The median pass time is, well, it's okay, it's not perfect, it's 18 milliseconds. I think that's fast enough to be usable, but we would like to improve that further. Now, in the very beginning, I said that our system is self-applicable. And this is really a cool feature to have, because it means that if you write a language extension, you don't need to go all the way down to our basic support for writing that, but you can define your own abstractions for helping you define new abstractions. And the core idea behind that is, well, SugarHaskell is an object language and a meta language simultaneously. And you use the object language part of SugarHaskell to write your application code, but you use the meta language part to write further extensions. And these extensions, they can apply to the object language part and the meta language part. So here are a couple of examples. You don't have to read this. So let's assume you don't like SDF. You want to reuse your existing ANTLER grammar. You can do that. What you do is you write a meta extension that supports the ANTLER grammar, the ANTLER syntax, as an alternative to SDF. You desugar your ANTLER grammar to SDF. And they can really just copy and paste an ANTLER grammar into a SugarHaskell module. And we have tried that with an existing SQL grammar that worked very well. What else you can do? Well, we actually already saw that. I said that in strategic rules you could have concrete syntax to help you write the transformation. But that's not really true because, well, in strategic they support it, but you have to extend the compiler kind of, and you have to have a configuration script, and well. So instead, what you can do in SugarHaskell is you write a library that extends the strategic to support concrete syntax inside the transformation rules. Well, finally, what you can also do is write a meta-DSL, like really domain-specific language for defining other domain-specific languages or language extensions. And we exemplified this in the paper using EBNF. But we generate multiple things from such an EBNF artifact. Here this describes the untyped lambda calculus. And you have concrete syntax roots, and behind these, in the curly braces, you have the abstract syntax node name. And we generate multiple things. First, we generate a data type declaration, where we have like one data type for each non-terminal, and for each constructor name, we have one constructor in the data type, pretty simple. Then we generate a parsec implementation of this grammar, and a read instance, and these will parse a string and produce an instance of the generated abstract data type. And well, this allows you in your Haskell program to now use this parser to parse. But well, finally, we produced a really interesting thing. We produced another Haskell extension from this artifact. And the way we do that is that we allow users to import the EBNF grammar and the meta extension that was generated from it, and now write inside the Haskell code their own concrete syntax to define instances of the algebraic data type that we generated. So you can write this instead of like writing all the constructors. That's the basic idea. And you can like splice in information, and you can use it in pattern matching, for instance, to implement a beta reduction rule. And well, you might think you can do all of this with classic quotation in template Haskell. But have you looked at the implementation? On the top right corner, this is the implementation of the extension. It's just like this small EBNF grammar, that's all. All right, so SugarHaskell is flexible and principled. I think this is the basic thing here. We are flexible, we support any context-free syntax, can be layout sensitive. Language extensions can be built in a self-applicable fashion, and these extensions often compose. If there's a conflict, you can typically like add another piece of clue code to fix it. But it's also principled because we scope extensions via the module system. And well, when you use Sugar, this is transparent to your clients, and this is essential because well, you can compile some of your files with SugarHaskell, but when you deploy them, your clients can use a standard THC compiler. We have built an IDE that is also extensible. It pros with your language extensions, for instance, to have some syntax coloring here. You can, well, I haven't talked about that, but you can use SugarHaskell to also implement domain-specific analyses. For instance, for this EBNF example we saw before, I implemented a small domain-specific analysis that checks for left recursion in the grammar. And well, you can find all the artifacts on our website, sugarhaskel.org. It's compiler, the IDE, the case studies, but also the parser, which is usable as an independent component. And well, finally, I would like to say that if you want to extend Haskell syntax, I think it's a very good idea to consider SugarHaskell, because it allows you to kind of get the same amount of freedom as if you would implement a real GHC extension, but it gives you like a platform for experimentation. But also, if you need syntactic abstraction, you can use SugarHaskell because you get the same kind of flexibility without the syntactic boilerplate and the syntactic ugliness that you otherwise would inherit. But finally, that was our original motivation. If you want to embed domain-specific languages, SugarHaskell is just great because you get domain-specific syntax. Thank you very much.